Okay, in the last video, these boards had just arrived along with the parts, and I said I was going to build them. So I got a bunch put together right now. I was going to try to get some oscilloscope readings of the system now as part of an effort to get the right voltages on the capacitors. Okay, so here's the setup. I've got the newest pyramid eel instrument here. I've got the 4 new voltage doubling rectifier boards here. This one is hooked up to the instrument on the input, so we're going to have the stepper motors filling these caps, and the output is going to this scope here. Okay, so let's try the first pump with no load. I'm going to go relatively slow at first, and that got us about 15 volts so far without really trying. Another pump got us to about 12. Now we're nearing 20. So it looks like we could easily get to 20. You just have to make sure to set the probe to 10x. So I've set it on the scope and on the probe, and you can see we're up at 40 volts. See how much higher it'll go. So these are some pretty quick strokes here, and you can see it's not getting much higher. So that's about the most we're ever going to see with a pretty decent stroke. Not saying you can't He-Man it or something, but 45 I would consider open circuit. I would consider the operating range of this. So now let's do something fun. Let's empty the voltage. By the way, these are 2200 microfarad capacitors. Every single one of these is stocked with a different size pair of capacitors. And now let's dissipate. Oh. Woo! All right. Now, as interesting as that is, that's not a super realistic test, because we're not going to be getting up to 45, 50 high volts very often, because most of the time the instrument is going to be using up a lot of that voltage immediately in the output of the speaker. Not saying it could never happen, but I think that starts to give us the upper range of our capacitors. So if we're seeing, just call it 50 volts, kind of typically high on both sides, then that's going to be, if we're using one pair of these things, that's going to be 25 volts per side. I think, yeah, these happen to be 25 volt electrolytics. Yeah. Oh, that one's a 35 volt. See, that's the smallest one. That's the 1500. We've got the 4700. So what I'm eventually going to do is have all the 4 phases in the system hooked up at once. That's why there are 4 of them for the 2 stepper motors. Anyway, let's try it with a different kind of experiment. Let's put a different load on there. Let's put the speaker as the load. Now note, that's also kind of unrealistic, because it's pretty rare that we'll be driving directly through the speaker at exactly 100% of the input energy. But actually, I think it'll be more common than we think, now that I think about it. You always want to save a little bit of power around, but anyway, let's just give this a shot and see where it ends up. Okay, so all I've done here is I've used alligator clips to put the roughly 8 or 4 ohm speaker in parallel with the voltage doubling rectifier's output, and we're looking at the scope. I have not changed the scale of it yet, so see the signal is quite small. Let's zoom in on that a little bit. Okay, I've lowered the scale down to 1 volt. Now, interestingly, we're only seeing about 2 volts. I think that may be because the load is kind of high, although I would have expected it to decay a little bit more slowly than that. Granted, there is some decay. Yeah, it's kind of a small decay. That would be one of the reasons to choose larger capacitors, actually, to actually hit that voltage point a little later with more charge in there. So this is the most loaded one here. You know what would be really cool is if I could get that second axis going so that we can actually compare them side by side. Okay, I zoomed in time so we could get a closer look at this. One of the things I found interesting is that when we speed up, the peak-to-peak amplitude of the sinusoid signal goes down by quite a bit. See there, the amplitude is very small, but at the lower speeds, we at least have some range. So if we were to look closely at that, we would probably see the shape of a sort of type of scallop shell, a sinusoid coming out of the generator, going into the charging capacitor, reaching the peak, and then allowing the capacitor to dissipate against the load of the speaker. Of course, this is not a very ideal load to do this with. The speaker's a very complex load. But I think this also brings me another exciting memory of when I was doing this project many years ago. I found out that driving these speaker waveforms at the full voltage gathered by the capacitors resulted in a very inefficient signal. It was only when I had a duty cycle, when I sent pulse waves with a duty cycle of around 1/8 or 10, 15% that I suddenly saw a humongous increase in volume. And so it took a long time to figure out why that is. But if you look closely at this plot, then you can almost see what it's about. That's the charge cycle, and this is the discharge cycle. That's because in the circuit diagram for the voltage rectifier, there are diodes doing the rectification, which are only letting the current flow. So the effect is that the capacitors only get charged when the incoming voltage is greater than the current voltage, and the charged voltage of the capacitors, the main capacitors, as I call it, VC. So in other words, if this doesn't dissipate quickly, if you don't use up that charge that you've accumulated, if you don't dissipate it before the cycle gets low, then you don't get the benefit of that movement in the charge. Basically, when the flux is created, it sees an open impedance at the electrical side, and so it doesn't flow into current. And then when the switch is closed, when the diode is on, the charge cycle is quite fast. So in other words, you have to kind of save up a bunch of charge on the millisecond level and then dissipate it. So you can do sort of save up the charge for about 7 to 1 duty cycle. So in other words, you might charge up for 10 microseconds or dissipate for 10 microseconds after charging up for, say, 70 microseconds. And within that space, you can kind of use various techniques like, the biggest one would be just to vary the PWM around that range. Because what you're effectively doing is generating a gigantic impedance matching machine. You're trying to match the impedance of those motors. Once again, I'm going to try and capture the fast signal. There we go. So you see that's got a very tiny peak to peak compared to the slow one. By stacking these in series and in parallel, helping them charge faster, there are a lot of different configurations. So that's why it's nice to have these modular boards that have the voltage series connector there and duplicate of the DC voltage. It's not just for distribution, but you can measure it and debug with it and also use it to stack these configurations. And this is kind of what's necessary because, we're still discovering the operating range of these things. Motors are changing all the time. It's exciting. That's all for now.